Welcome to this video on the Introduction to Simplification for TEJ4M. Yesterday, we focused on writing Boolean expressions. Today, we will be discussing the simplification of these expressions. Complicated logic can be represented by arranging logic gates, but this is hard to draw. Boole developed a system for communicating this logic clearly using mathematical operators to represent arrangements of logic gates. This slide serves as a reminder of the various logic gates and their corresponding Boolean equations. Just as in standard math, the arrangement of operations matters. Brackets are sometimes necessary to achieve a specific logic when writing Boolean expressions. The key questions for today are, how do engineers make their inventions as cheap and simple as possible? And how can we determine if some gates can be eliminated from a device? Consider this circuit. Is it efficient? Is there a simpler circuit that can achieve the same result? We need to learn how to figure this out. To understand if this circuit is efficient, we must first determine its Boolean equation. Then we can explore if a simpler design exists. Here is the truth table for the circuit, where P and Q are the outputs of the initial OR gates. Look at the final output Y. Do you notice anything familiar about the relationship between inputs A and B and output Y? The truth table for our initial circuit actually matches the truth table for a single OR gate. This means we have found an equivalent, much simpler circuit. How can we find these revisions without having to draw a full truth table every single time? The ease of simplification is a major benefit of Boolean expressions. We can visualize operations similar to standard algebra and use a set of rules to help us simplify. Let's explore some of these simplifications. For example 1, A OR not A. Since one of the terms must be a 1, the result A plus not A will always be 1. This is one of many useful rules for simplifying Boolean equations. In Boolean algebra, many standard algebraic operations apply. The chosen symbols aid in remembering the laws of Boolean algebra. The commutative law states that the order of addition or multiplication does not matter. For example, A times B equals B times A, and A plus B equals B plus A. The distributive law expands expressions like A times B plus C to AB plus AC. Also, A plus B times C plus D equals AC plus AD plus BC plus BD. The associative law allows us to group terms differently without changing the result. For addition, A plus the sum of B and C equals the sum of A and B plus C. Similarly, ABC can be grouped as AB times C or A times BC. The factoring law is the reverse of the distributive law. It has useful applications, such as factoring out a variable. For instance, A plus AB simplifies to A. This slide provides a summary of the fundamental laws and theorems used in Boolean simplification. Truth tables can be used to investigate and verify Boolean equations, just like with logic gate combinations. Substitute values for each variable to compare the results. Here is an example equation. Y equals the quantity A plus B times the quantity A plus C. We can use a truth table to find the output Y for all input combinations. This slide continues the truth table example for Y equals the quantity A plus B times the quantity A plus C times C. Note the additional C term here. A more concise way to communicate circuit logic is through Boolean equations. Truth tables apply to Boolean equations the same way they do circuits. Remember that the order of operations in brackets are critical. Your homework is the simplification assignment. Thank you for watching this video. The listed resource was used in its creation.